Hello everyone, my name is Julian Nakalema, a student of Software Engineering Year 3, and I'm here to share with you an overview of what I got as an understanding in my machine learning course. So to begin with, what is machine learning? Machine learning is a field of study that gives computers the ability to learn without being explicitly programmed. That is, the computers learn on their own. We don't have to program them so as they can do what we want them to do. So that is machine learning, a brief definition. Whereas with the difference between machine learning and traditional programming is that with machine learning, the algorithms learn on their own, whereas with traditional programming, you actually have to program to give it rules to follow. So why machine learning? Now, there is a trade-off between data and rules. When we have too many rules to follow, we prefer to use machine learning. So in case of too much data and rules, we deploy a machine learning algorithm instead of traditional programming. This is because the algorithm can learn from the data, and its learning can help write rules. So when we have a lot of data, for example, maybe we are having to describe a position of someone, it may be hard to describe the rules, but we can just have images and we feed that algorithm with the images, and for it will come up with its own rules and accuracy. So we have types of machine learning. There are two, that is supervised and unsupervised. With supervised, we have human labeled data. Then with unsupervised, the data is not labeled. Although it's not labeled, it has the features that help the algorithm to learn. So now we have end-to-end machine learning. So this is the entire process of building a machine learning model. We have different steps. We define the problem and correct relevant data. When we are to work with a machine learning algorithm, before we deploy it and know which algorithm we are to use, we need to understand the problem that we are dealing with. After understanding that problem, we collect the relevant data. Then we go in to process the data. Processing, we have to clean it to have good data. So we need to go through that. Then we have to train and evaluate. Then we deploy and monitor. Then we have exploratory data analysis. I will say in simple terms, we are going through the data set that we have to see what exactly it looks like. What data are we being given to deal with? So this refers to understanding and analyzing the data to identify patterns, relation, and issues. Then the steps involved, we have to understand data distribution and relationships. We handle the missing values and outliers. We visualize the data. Then we identify patterns and correlations. Feature scaling. It refers to the act of rescaling numerical features to a common range to improve model performance. We can have numerical features, but we have some values that are so far from the others. So we normalize them to improve on the model performance and convergence. Data cleaning. So data cleaning, remember we said in exploratory data analysis, we are trying to see the kind of data we have. How does our data look like? What does it look like? But with the data cleaning, we now come in to address the problems that we find in our data. Sometimes we find missing values, we find duplicates, we find outliers. Now an outlier is like a value that is beyond the normal. For example, if maybe in a class of nursery kids are normally in the range of 3 to 6, maximum 6, 7. When you find someone who is 15 years in a nursery class data, then that is an outlier. Something is wrong with the data set that you're dealing with. So that we remove the outliers using the different methods. We handle the missing values using the different methods. Then we have feature engineering. So after cleaning our data, we now have a clean data set. So we have good quality data that we can actually work with. But even with a good quality data, we may have some features that don't make sense. We have to actually create new features in that data that we have so as to have sensible results and sensible visuals. So that is what we call feature engineering. So it's the process of creating, transforming, and selecting features to improve model performance. Linear regression. Linear regression predicts continuous output variable. Models relationship. It also models the relationship between dependent and independent variables. Its goal is to minimize error to find best fit line. That's the line of best fit. Yeah. Parametric and non-parametric models. With parametric models, you actually know which model will fit the data. You have defined number of parameters. Now with non-parametric, it's the other way around. The data defines, it's what tells you what the regression should look like, and then the number of parameters are unknown. They're actually defined by the data itself. We have the KNN. KNN is the key nearest neighbors. So the steps include, we have to calculate the distance between all the training data and the test point. I have some illustration below here. Let me lift this up a little. Now, this is the blue point, that one is the data point that we are looking at. And we have category A and category B. So we look for we calculate the distance that is between this point and each of the training data. And then after, we get the key nearest neighbors. Then what this point is obtained based on a majority vote, i.e., the more the kind of the neighbors, that is what the point is. So that's why we realize that here our point actually takes on the look of category A. Yeah. So that is KNN. Let me bring this back and proceed with the video. Then we have hyperparameter tuning. So we tune hyperparameters using a third dataset, that is the validation dataset. So here we have the training, the test, and the validation dataset. We cannot use the test dataset to hypertune because the goal of machine learning is to perform well on unseen data. So now when we hypertune using the test dataset, then this is losing meaning. So we have a small dataset called the validation dataset. So here we have 3 datasets. We have the training dataset, the test dataset, and the validation dataset that we use for hyperparameter tuning. We have Manhattan versus Euclidean distance. Manhattan distance is the sum of absolute distances. It is used if dimensions are dissimilar, i.e., we can just say the distance x2 minus x1 plus y1 minus y2, such distances. Now with the Euclidean distance, it is the straight line distance. It is used if dimensions measure similar properties. I'll give an example of Pythagoras theorem. When we want the hypotenuse length, we get the square root of the 2 sides. So that is an Euclidean distance. It's straight line distance, but it is used if the dimensions measure similar properties. So whenever the dimensions are dissimilar, we opt for Manhattan distance. The advantages of the k nearest neighbors. It is easy to explain, simple to understand, and extremely powerful. Very easy, even when you just look at a visual of it, it's very easy to know. You can easily use it with multi-class datasets. You can use it for both regression and classification problems. It does not require any assumptions on the data distribution. Then the disadvantages. Anything has advantages and disadvantages. So it cannot work if there are any missing values. You will actually be misled because you will miss out on remember we compare that it's a majority vote. So if we are having some missing data, we shall actually have inconsistencies. It comes at a cost of making the prediction step relatively expensive. The efficiency of the algorithm declines very fast as the data set grows. So remember, we are measuring these paired distances and we are comparing them to get the nearest neighbor. So if we are having a huger data set, that means we take much more time in calculating these distances. Hence, the efficiency of this algorithm declining. Yeah. Gini impurity and decision trees. Gini impurity, it measures the frequency of mislabeling when randomly labeling a data set elements. Then it ranges from 0 to 0.5. Then we have the entropy range, which is 0 to 1. Then pre-pruning. Pre-pruning controls tree growth. Information gain. This is just a summary. Information gain is biased towards attributes with many outcomes. Advantages of decision trees. They're easy to interpret and visualize. They are non-parametric, no distribution assumptions, captures nonlinear patterns, requires minimal data pre-processing, versatile for feature engineering and handling various input and output types. So now we have the random forest algorithm. Below, this is an image of our random forest algorithm. This is an ensemble learning technique that combines multiple decision trees. It combines multiple decision trees. As we see here, we are having multiple. We have decision tree 1, we have 2, we have 3, and they're all being combined into one. So that's what we call a random forest algorithm. So the pros of random forest, that is the advantages. It's robust to outliers. It performs well with nonlinear relations between features. It lowers the risk of overfitting. It can handle large data sets efficiently. Then its disadvantages, as we said, anything with advantages has disadvantages. It's biased with categorical variables, slow training. It's not suitable for linear methods with sparse features. And then it has greedy algorithms. Then we have boosting versus badging. Boosting, it is here that trees are grown with weighted samples. Boosting is a sequential technique where trees are grown with weighted samples. Whereas for badging, trees are grown with subsamples. It creates different models using bootstrapped training sets and averages predictions. Then we have the SVM. SVM in full, it's the support vector machines. It prioritizes correct classification over margin maximization. It detects outliers. The kernel function defines similarity in transformed space. Then gamma is a hyperparameter that controls the influence of a training point. So the gamma can either be high or low. Yeah, it can either be high or low. And when it's too high, when it's too low, it also has its consequences here and there, but it can either be high or low. Then SVM, it's a support vector machine. Yeah. Then we have PCA. PCA is the principal component analysis. Principal component analysis. It reduces data dimensionality with minimal information loss. Then it assumes linear correlation. After it assuming linear correlation, let me first go back slowly a bit about this gamma to give a highlight. High gamma requires points to be very close to be in the same group, risking overfitting. So when it's high gamma, we have a risk of overfitting there. Whereas with low gamma, it indicates a large similarity radius, grouping more points together.